Okay, so today's webinar for GMI will be technical on the architectural constraint according to the two leading standards, the functional safety standard IEC61511 and the IEC61508. And we are waiting until a few more participants are coming in. So good morning, good afternoon, or good evening, wherever you are based. Welcome to our webinar again. I'm sharing this today with my colleague Gabriele from GM International. And I think Gabriele, as the attendees are starting to slow down to join us, so you can probably slowly start to introduce.
Okay, that's good. So hello and welcome everybody to this webinar about how to deal with minimum architecture constraints. This is one of the many topics that we cover during this kind of events, and considering the good feedback that we received so far from the participants, we continue sharing our knowledge regarding intrinsic safety and functional safety. Just a brief introduction about myself. I'm Gabriele Caglio. I'm a technical support specialist at GMI, and Tino Van de Capelle, which is the functional safety expert, and today's main speaker. I would like to start with a brief introduction of GMI. For who doesn't know us, GMI is an Italian company. Yeah? Providing field interfaces related to intrinsic safety and functional safety. This means that it's possible to find GMI devices in many industrial packages such as BCS, ESD, fire and gas, and so on. As you can see on the screen, we are talking about oil and gas, petrochemical, pharmaceutical, mining, but also food and beverage and many other industries. We have 40 years of experience in the field. The headquarters, as I said, is in Italy, where we have our main facility and where we design, produce, and test all our products. As you can see now, we also have several offices and resellers all around the globe, so we are pretty much available everywhere. As mentioned before, we are a safety company, and we aim to provide safety and reduce the risk of hazardous events to safeguard people, assets, infrastructure, production processes, and the environment too. For this reason, the quality aspect of our product cannot be overlooked. We design our product, we manufacture and test 100% our devices internally, meaning that we do not outsource any of these tests. This is why we are confident with the quality of our products. Couple more quick slides before to get to the real part of the webinar. This is about the certificate we have, or at least the certification bodies we deal with. This guarantee the quality of the device, but also guarantee that GMI products comply the market requirements according to different local regulations. Something about our portfolio. We have, as I said, intrinsically safe barriers, safety relays, certified seal, with and without line monitoring to energize to safe and non-energize to safe application. We have isolators, AX power supply system up to C3, temperature and digital multiplexer for zone 1 installation. We also have customized termination board for an easy connection to the main PLC and VCS system, ARC multiplexers, surge arrestors. And we also provide consultancy and share our experience through our courses related to, as I said, functional safety and intrinsic safety. The last slide. It's the list of our customers, which stretch from system vendors to EPC, OEM, and end user. That's pretty much my introduction of the company. Just the last thing I would like to say is about the webinar, which it means that it's registered. So in a few days, you will be able to find it on our YouTube channel. So if you subscribe, you will get a notification too. You will get a link to download the PDF copy of the presentation, and Tina is going to show you. You also get a certificate, but only if you attend at least 75% of the webinar. And if you have any question during the presentation, please write it down in the Q&A session, and we will try to answer to all of your questions. And I think it's everything from my side. So please, Tino, go ahead.
All right. Thank you, Gabriele, and thank you, GMI, for giving us another opportunity to share some of our know-how. We have done many before, as Gabriele is saying. The sessions are always recorded. We have a dedicated YouTube channel on GMI, on GM International, and that is where you can find all the pre-recorded sessions, including also this one will be online. Today's topic is a technical topic. It's coming from the IEC standards, from the 61508, which is known as the Functional Safety Standard for EEPS. That stands for Electrical, Electronical, and Programmable Electronical Safety-Related Systems, which is in fact the standard that GMI is using to develop their hardware and software in their devices that Gabriele was just showing. The second standard related is the application dedicated standard for the process industry. And as the applications were also shown on the introduction from GMI, the process industry for 61511 is still the oil and gas, chemicals, petrochemicals, and new by edition 2, which we still call it new, although today it's 8 years new. That means 2016-17 release of the edition 2 has added 2 new applications, which is the food and beverage and also the pharmaceutical. I start off here with the life cycle. I don't have the intention to explain the complete or entire life cycle, but for the manufacturer like GMI, if GMI has a target in the market segment to supply you with an interface which goes into the SIL 1 criteria or into the SIL 2 criteria or into the SIL 3 criteria, that means that that specific criteria for SIL 1, 2, 3 may have some different, let's say, technical requirements that GMI will have to prove that they follow when they claim compliance with the IEC61508. And the IEC61508 has a life cycle approach. That is the one that you're looking at now here on this slide. And the life cycle, as you can see here in the middle, when I hover here with my cursor, we have 16 boxes. We call that phases. And they start from phase 1, from the concept, all the way to the phase 16 of the decommissioning of that interface from GMI. Well, as you can see, when they start from the concept, they go into the overall scope definition. There is a need to do some hazard and risk analysis specific of the interface that GMI will develop. Of course, there will be a safety requirements that needs to be written out or needs to be dedicated, that the hardware and software developers in the development team from GMI will know exactly what they have to develop. That is where we go into the requirement specification here in phase number 9. And then physically, they go into the, let's say, safety-related system development, as well as for hardware, as potentially for software. At the same time, they also have to think about how they will go into the installation and commissioning of such an interface, how this will be validated, how this will be tested at the end after the installation and commissioning, and also later on for the end users, especially for the end users, how can they operate and maintain a safe, let's say, reliable working interface from GM International. That's where phase 6, 7, 8 goes hand in hand together with phase 12, 13, and 14, which is the eventually, after the installation commissioning, is the ops and maintenance for the end users. Here you have an overall modification and a retrofit. That is, if potentially in the interface from GMI, there would be a modification or retrofit possible or needed, there they have to go to the appropriate phases in front here of the life cycle. Well, all this life cycle is what actually GMI has to follow in terms of developing and delivering their products to the field. That needs to be functional safety managed. That is why the 61508 is also having a functional safety management requirement for GM International. And GM International on their products, and you have seen a list of certification that Gabriele has showed you. That is where they also prove that they have a systematic capability. And the systematic capability that GMI typically will try to achieve is SC3. That means you are actually allowed to use the interfaces in a environment up to SIL 3. And that's all what I want to give you here as a highlight on the life cycle of the 61508. So once the developers are being required to develop a SIL 1 or a SIL 2 or a SIL 3 interface, they have to fulfill some technical criteria from the IEC 61508. And one of them is called HFT, which stands for the hardware fault tolerance. In other words, how many danger faults can your interface tolerate and still achieve safety? You heard that Gabriele was mentioning there are some safety relays, including also with line monitoring. That means that when the safety relay is being used as an interface between your control system and between your final element or between your final load in the field, that means that the interposing relay, as we typically refer them to, needs to be able to either switch off the power or switch on the power when needed. Able to do so, the IEC 61508 will require, according to a certain SIL level, to fulfill a minimum architectural constraint. And the minimum architectural constraint is typically what we will express in an HFT or a hardware fault tolerance equal to either 0, equal to 1, or equal to 2. If you will see, for instance, in hardware fault tolerance equal to 1, that means the interface itself, internal kitchen of the interface, needs to be able to tolerate one danger failure and still achieve safety. So typically, if you would have a normally open contact, that means we can remove the power to the field, the internal integrity of the system, of the interface from GMI will be able to actually switch off by multiple contacts the power to the field. That means they will go by an HFT of 1 by using 2 contacts in series. If one contact cannot go open, then the other contact can actually potentially remove the power to the field. The minimum HFT as per the 61508 will be divided into 2 decision groups. One will be the road 1H, and the road 1H, that means that this will be the definition that I will explain you in a minute, which I will show you in a table. Road 1H is coming from the initial edition 1 of the 61508 from 1998. And in 1997, 1998, exactly when the 61508 edition 1 came out, there was only this Road 1H available. And Road 1H will always look on what safe failure fraction that interface potentially can achieve. Road 2H by 61508 is quality proven in use. That means the manufacturer can collect some field data from installed base, and based on the collected quantity and quality of data, they can claim a proven in use. The 61508, which is the second edition, 2010. If you look in part number 2, which is the hardware section, it's called Hardware Safety Integrity Architectural Constraint. There are 2 potential roads, which I just mentioned. One is called the Road 1H, which is mainly driven by the safe failure fraction, and they will use this tables 2 and 3, which again will be shown later on here in the webinar. Table 2 is known as the type A devices, and table 3 is known as the type B devices. Road 2H, as I already mentioned, is based on quality feedback coming from the field, and this is coming from end users installed base that the manufacturers will try to collect and which will then be decided. In the meantime, I'm reading here a question coming in. Are SIL above 3 not covered under the IEC 61508? Well, actually, SIL 4 is also covered. Both SIL 4 in the 61511 and in the 61508 are also covered. As you will notice, there is a table with 4 SIL levels in both standards. However, the interfaces that GMI has on the market goes up to maximum SIL 3. That is why in my story, I only limit myself to mention you up to SIL 3, but indeed we can also have SIL 4, as you see here already on this page. That's here the table, which is table 2 and 3. Table 2 Oops, I was just trying to click that I answered lively. Let me go back. All right, sorry for that. So table 2 and 3, type A is table 2. What is a type A? When all the failure modes are well defined and can be 100% determined if they fail, how they will fail, and also there is sufficient data available. Sufficient data available in the edition number 1, which was the 1998 edition of the 61508, means that sufficient data was 100,000 hours of field experience with 1 year service record in 10 different applications. They have changed that in the edition 2. Edition 2 will talk about 90% of a confidence factor that you have your data uncertainties needs to be covered in your failure data, but I will come back on this when I will mention the road 2H. Let's first stick to road 1H. If I give an example, let's assume that GMI will come up on the market with a new product and there is no install base yet. How can they determine how reliable a certain device will be? Most likely, if it is a hardware device, they will do only an FMEA or an FMEDA. That means a failure mode and effect analysis. And on the failure mode and effect analysis, they will try to come up with a quantity of how many dangerous and how many safe failures are potentially in a particular interface. That will lead into an equation which we call safe failure fraction. And safe failure fraction will represent a ratio of the hidden danger undetected failures in a system. And as you can see here on the left column, it can either be the safe failure fraction or it can be also the built-in diagnostic coverage in a system. For some of the attendees here listening into this webinar, you may use a safety PLC as an example, and the majority of the safety PLCs will claim that they have a diagnostic coverage of 99.9%. That means those safety PLC manufacturers will sit on the bottom row, which is here more than 99% coverage of diagnostics. A typical interface, which is a SIL tree interface, like GMI has on the market, many of them will have a range of a safe failure fraction, anything between 90 to 99%. And if I would take a safety relay from GMI, which says the majority is a SIL tree relay, then you will see that with an HFT of 0, which is the column here, the first column in table number 2, you see here a 0. That's represent the hardware fault tolerance or the HFT. That is the reason why a GMI relay can achieve a SIL tree with a single device. Assume that the interface from GMI would only have a safe failure fraction between 60% to 90%, and that is, for instance, a SIL2 relay. Well, then you will see with that one interface, they can achieve with a single relay, which is an HFT of 0, they can achieve a SIL2. And if GMI, and I do believe that GMI does not have a range below 60%, because then they would limit themselves that to a single interface, it can only go up to SIL1. And how does it work? If you look here, if I would take a SIL2 relay, and I would have here a safe failure fraction anything between 60 to 90%, and I would add an additional relay in series with the first relay, that means I would create a HFT of 1. That means I would create a 1 out of 2 interface. I take 2 relays. I could claim a SIL tree application based on type A with a safe failure fraction anything between 60 to maximum 90%. If I go into type B, what is a classical type B? When the failure modes are not well defined, or there is not sufficient data, or there is an integrated circuit in there with a firmware-based device, such as a smart transmitter, such as a hard transmitter, as an example. If you take all your smart and hard transmitters that you potentially find on the market today, they will claim a SIL2 with a single smart transmitter. And if you would look in the safe failure fraction that they would have claimed or diagnostic coverage, they probably will be sitting anywhere between 90 to 99%. And then in theory, if you would take the table 3 or the type B, and I would take two smart transmitters SIL2 together, I could potentially claim SIL3 only if my systematic capability will be SC3 in this particular example, which I've been just giving you here. I'm going over now into the 61511. The 61511 life cycle is the life cycle that most of the end users or most of the system integrators building safety instrumented systems for the process industry will follow. And we have the same approach. In the middle of the life cycle, you see here again 8 boxes. The boxes, we call that phases. We go from phase 1 into phase 2. And the topic for today, the architectural constraint, only comes into question in phase number 3 and potentially in phase number 4. That means phase number 3 is called the safety requirement specification. So once you have done your hazard risk analysis in phase number 1, and potentially you have done a LOPA, layer of protection analysis, that means you will allocate specific safety function to existing layers. That is where you will come to the conclusion, do we need additional risk reduction, yes or no? Assume that you need additional risk reduction and assume that you want to build a safety loop. And in that safety loop, you will use one of the safety interfaces from GMI as an example. Well, once you write your safety requirement specification that you will define what additional risk reduction do we need, and you would, for instance, need an additional SIL3 loop, that means that loop needs to be defined. And in the safety requirement specification, and we also have a webinar on this, there are 29 items that the new addition 2 from the 61511 will require you to describe. You shall include and you shall describe as applicable. One of the interfaces, one of the subsystems of your safety loop, maybe the safety relay, or maybe as an example that Gabriele was giving, your safety barrier or your safety isolator. That is where it will be specified in here in your safety requirement specification. So eventually in phase number 4, that is where you will start to contact the GMI, let's say, representative or your agents. And that is where you will actually start to search a solution to fulfill your requirements, which were specified here in phase number 3. If I go here into my design and engineering of a safety instrumented physical system, that is where you will have to understand your hardware fault tolerance requirements. Because maybe the interface that you are looking for is not available in that, let's say, version of level of SIL on the market, and maybe you have to create your own architecture with adding multiple instruments maybe together, as an example. That means that the design and engineering of safety instrumented system is where you will have to understand the limitation of both the 61508 architectural constraint and or the limitation of the 61511. The 61511, as I said, is for the end users. They also call it the hardware safety integrity architectural constraint. It's the same indicator, it's the same HFT, it's the same 0, the same 1, or the same number 2 that you will see as we have just shown you in table 2 and 3 from the IEC61508. The SIS shall have a minimum HFT with respect to the safety instrumented function that you try to implement. And of course, your safety instrumented system can be split into independent subsystems. That means one safety loop may have independent subsystems, whereas one of them was that safety relay, one of them would be that safety interface being your isolator or being your barrier. And the 61511, let me be very clear on this, the 61511, when the edition 2 came out, in 2016, 2017, if there would be someone already here from the USA listening into the webinar, you are using it as the IEC61511, and that was been applicable on the 2018 release in the US. Well, both of them, the 61511 IEC and ISA, they do prefer prior use data. And prior use data is not the same as proven in use. Prior use data means from the end user field further feedback, not from the manufacturer. Eventually, the manufacturer can only receive the same data as the end user already has collected. But this will be shown later on here on my next slide. I call this here my method number 3. That is my personal definition. That's not coming out of the standard, but that's called the prior use preference, which is based on quality fair feedback, not to use the safe value fraction subsystems like we have done in the Road 1H, which again I will show you on my next slide as method number 1. So eventually you as an end user or a system integrator or someone who will start to create a solution to build a safety intermittent function, there are 3 options there for you. Option number 1 is based purely on the manufacturer data, which is I almost said Entweder, which is now German. I was just speaking German before. So it's either safe value fraction, or it will be diagnostic coverage, which will be then looking into your table 2 or table 3, which is type A or type B. And that will be your definition on how many do I need in order for me to achieve a certain SIL level. Option number 2, which is the middle one here, that is method number 2, which needs quality fair feedback data that had to be collected by the manufacturers. But if the end users do not collect good data, typically the manufacturer also will not get good fair feedback data from their devices. And I give you a very simple example. Assume that you buy an interface that costs you $100 or €100, and the interface is out of warranty and the interface is failing. Most likely you will replace the broken or failing instrument or interface with a new one, and you will toss or you will trash your old, broken, or not working or correct functioning interface. That means the interface manufacturer may sell you a new interface not knowing that the previous interface has not working correctly. That means maybe the manufacturer may not know the exact real data, as the feedback from the end users is typically failing when the interface costs more money to send it back to the manufacturer by courier than to buy a new one. So in other words, fair feedback data is a bit of take it with a pinch of salt. It could be applicable. It could be very hard to believe or understand how the data came from. Method number 3, that's the last one, is called quality fair feedback data. Again, the same quality feedback data that the end users will need to collect, and there will be some guidance giving in the IEC61511 or the ISA61511, which are the 2 guidance coming from the Namur NE130 or from the ISA Technical Report 4, which has been newly released in 2020, and the NE 130 from Namur has been newly released, again updated revision in I think July 2023 or September 2023. So it's very recently that has been released again in a newer revision. The SIL level itself will be determined what and how many HFT you will need if you follow the 61511. You're looking here at the table 6. So I showed you before table 2 and 3 from the 61508. This one here is known as table 6 from the 61511. And table 6 will be again telling you the minimum HFT according to the SIL. In other words, you look on what type of level of SIL do you need. If you, for instance, I give you an example, you need a SIL 2. The second answer that you will need to be able to answer before you will be selecting the correct architecture is it is either a low demand mode of a safety function, or it is a high demand or a continuous mode. If it is a low demand mode, that means your safety function will be only demanded that the hazard is happening no more than once per year. So no more than once per year will be called a low demand mode, and then the standard will allow you to use an HFT equal to 1. That means you can then say, I will use my device, which is here on table 6 based on prior use or proven in use. I can use my HFT equal to 0. If the hazard would happen more than once per year, that would become a high demand mode, then the standard will require you to go to an HFT equal to 1, as you can see over here where my cursor is hovering. If you would go for a SIL 3, regardless what mode of operation that your safety loop would be in, if it would be a low demand, high demand, or even a continuous mode, then you always are required to install minimum a HFT equal to 1. That means you always have to have a redundant solution for SIL 3. So if you think about your final elements, and if you're using a single valve is only applicable for a SIL 2 low demand mode. If you would have a high demand mode, then you will have to have a dual installation with 2 valves. If it is a fail to close valve, it will be a 1 out of 2 fail to close valve enabled to isolate the stream in this pipeline. Right, Gabriele, we have the first poll coming up, and I will read the poll for you. So we want to have some interaction from our attendees, which is a big group today. So we hope to have at least 50% of some interaction. Can you launch the poll, Gabriele?
Yes, sure.
So the question for you is the architectural constraint according to the 61511. Option number 1, which is here A, can use either, let me just move the poll window a bit aside so I can read the question again. So A can use either method 1 or method 2 or method 3, but only one method per safety instrumented function is applicable. Answer B, can use method 2 and method 3. For those who forgot what method 2 and 3 was, that method 2 was proven in use, method 3 was prior use, both based on row to H mixed per SIF. C can use only row 1H when claiming prior use for the 61511. And answer D can mix per safety instrument function all the methods. That means method number 1, which is based on safe failure fraction or diagnostic coverage. Method number 2, which is proved in use. And method 3, which is prior use, per SIF, all as applicable. Okay, so we need some interaction. So we need you to wake up for those who are already asleep. And we want you to click. There is no money to win. There is no face to lose. It's just to see for us there is some interaction coming from the group that we are doing the effort to bring you some awareness of functional safety today. And we need a few more clicks, so don't be shy and don't be afraid. Okay, so we are getting there slowly but surely. We still need a few more clicks. Otherwise, I go in strike. I don't want to continue if you don't click. Okay, I think that is helping us.
Okay,
I think
so
we can close the poll.
poll.
Really,
3, 2, 1. Okay, here we are.
You could share the results if you want. Okay.
Yes.
So, unfortunately, the majority today is clicking the wrong answer, which is not the... Excuse me. I was drinking water, and I think I have to drink some more. Okay. So the majority is clicking the wrong answer, which is saying that you can either use this method 1 or method 2 or method 3, but only one per safety loop. Well, if this would be true, that would be great in the industry, but unfortunately, this is not true at all. The reason is very simple. All different manufacturers are all using different approaches on how to come to the, let's say, assessment of their equipment to prove they are complying to a certain SILA. So the majority of smart and hard, but to give an example, will all be on row 2H today. The minority will be on row 1H. All the new products on the market typically can only enter the market on row 1H. Traditionally in the industry was row 1H. That means that the safety PLCs majority will all be on row 1H. The majority of all the interfaces from GMI traditionally are also all on row 1H. So there are not so many road to 8s in the interfaces from GMI for the moment yet. That may come in the future. But the right answer should have been here, the last one. That means you can mix. You can mix here the method 1 and method 2 and method 3 all as applicable, and I will show you the reason why this is on one of my next slides. Oops. So what is hardware fault tolerance for you? If you see in the future an HFT of 0 and you are only after safety availability, nothing to do with production or process availability. Well, if you're only after safety availability, a HFT of 0 can be achieved with a 1 out of 1. Of course, if the process people, production people, they want to also maintain production availability, that HFT 0 needs to be built with a 2 out of 2. And I will show you some practical example later on one of my slides. If you will see an HFT requirement equal to 1, that means the minimum architectural constraint for safety availability will be built with a 1 out of 2. And as you may have seen in the industry, many 2 out of 3 on the sensing or sensors elements, like your smart and hard transmitter. You may have asked maybe the question, why do we use 3 transmitters? Because for safety point of view, 2 transmitters in a 1 out of 2 are giving you the same safety availability. The differentiator will be here that once you are selecting a 2 out of 3 is that you want both safety availability and you also want to have production availability, and that's when you will go into a 2 out of 3. We have another webinar in GMI where we will explain you the difference between a 1 out of 2 and a 2 out of 3 more in detail, because there are some subtle differences that you need to understand before you make that decision. And if you would see a requirement for an HFT equal to 2, which is the maximum HFT that the 2 standards today, current standards, are asking, the IEC61508 and the IEC61511, then you will have to have a 1 out of 3. For instance, a SIL3 relay from GMI with a normally open contact means the internal kitchen of the relay will have 3 contacts in series with each other. That means GMI has achieved internally an HFT of 2 by adding 3 contacts in series with each other. That means either one of them, 1 out of the 3 contacts, can open to remove the load to the field. For the end user, the relay is still 1 contact, 1 load that you can open. Internal kitchen is 3 contacts enabled to achieve this HFT of 2 as a requirement from the IEC61508. A 2 out of 4 is the same as a 1 out of 3 in terms of safety availability with a increased production availability. That means production availability, all of those configurations in the right column can tolerate 1 spurious strip or 1 nuisance strip, and you still maintain your production availability. The middle one here cannot tolerate any spurious strip or any nuisance strip. They can only tolerate a dangerous hardware failure in this architecture. That means that a 0 can tolerate 0 hardware failures, a 1 can tolerate 1 danger failure and still achieve safety, and the last one here, a HFT of 2, means you can tolerate here in a 1 out of 3, you can tolerate 2 danger failures and still achieve your safety. And I give an example here in a reactor example. Assume that you have a chemical reactor and you have the feed of the reactor, the inlet over here with this 1 pipe. If I install 2 valves and both valves are failed to close, that means failed to close means closing is achieving safety. Enable for us to isolate the reactor from the inlet production feed line. We can close the first valve, or we can close the second valve, or we can close both valves. That architecture will be known in industry as a 1 out of 2. I can close either of the 2 valves and I can isolate the stream. That's a great solution for the safety people, because the safety people knows that if one of the two valves doesn't want to close and the other one is still closing, we can still achieve safety. Traditionally, production people don't like this, because if one of the two valves will close for no reason, that means a spirit strip or a nuisance strip, they will lose production. So my summary, a 1 of 2 is great for safety, but it is the worst solution for production availability. Opposite, take the same reactor, and now we're talking about draining the product. That means we want to drain the product. Once the reactor batch is finished, we want to drain it. And here you see a solution with, again, 2 valves, but now the valves are failed to open. That means enable for us to drain the product, we want to open the first valve, and we have to open the second valve. Why do we use 2 valves in a configuration called a 2 out of 2? Well, a 2 out of 2 is the worst solution for safety. Assume that the first valve is stuck closed, and I'm opening my second valve. I cannot drain my product, so I cannot achieve my safety if I need to, for instance, drain that product for safety reasons. So a 2 out of 2 is the worst for safety. Traditionally, again, production people will prefer that, because now they know if one valve is starting to leak, since my second valve is maybe still working correctly, they may not lose their production. So a 2 out of 2 is great for production availability. It is the worst one for safety, which is just the opposite than the left one. This was the worst one for production, but was the best one for safety. And here it's the best one for production, but the worst one for safety. Summary. Our webinar is coming to an end with a summary slide, and then we still have one more poll. What we have not told you yet, which I think I forgot to mention, we have collected some questions from people that did the registration. So the pre-recorded questions have been answered by me in a second presentation, which I will show you after I finish here with this one, and that will be then handled later on. So summary here, if you look to this slide, that's probably one of the better slides that you will see in the industry. Although I'm very humble, as I have made this slide myself, but that's one of the main slides that I'm using in teaching my training courses, which you may or may not know, but one of my main targets or main tasks still today is we are still providing you with the functional safety competency program from TUV Rijnmond. And I think I will reach the number of 3,000 engineers this year, 2024, that I've been training over the last 20 years. So I have done more than 200 trainings worldwide, and we are keep on going, so we haven't finished yet. Although some of the participants were sending me an email, when will you retire? Well, the good news is it's not for this year yet. I do not know how long I will continue, but I still find a passion and a pleasure to provide you with the trainings. So coming back on the slide, the hardware fault tolerance is actually here a summary. Which side of the branch do you select? Do you select the left one, which I call here method number 1? Do I select the middle one, which is called my method number 2? Or do I select the right one, which is indeed the preference for the 61511? Let's start with the right one. So we start with the last one, method number 3. Assume that you are an end user and you have to build a SIL loop. And the SIL loop needs to comply to SIL 2, as an example. How do you start? Well, first of all, you need to know what interfaces will you need to fulfill, let's say, the safety functionality. And assume in there you have, for instance, a safety PLC and you have to drive a solenoid. And the safety PLC digital output, for instance, cannot drive the load which is required in the field. You will have to find an interface. And one of these interfaces may be your safety relay. And your safety relay is, for instance, the one that you will have to search on the market. Well, the first one that you will have to look for is The safety relay is the relay which you have already in the field that you have been using before, which you may have some data, your own data. That means we are first explaining you here the example that you select an interface which is based on your own experience with your own field data experience from an install base. That means this is called the famous prior use. So the prior use is an end user collecting data based on this report number 4, which has been revised. The correct date should be here 2020, so the slide needs to be updated also into 2020, but it doesn't really matter. It's still the report 84, report number 4, which has been revised based on the edition 2, which is in the US, the 2020 release of report 4 of the 84 committee. And or you will use the Namur 130, which has been revised, as I mentioned already in the introduction, somewhere in the 2023 time frame between July and September. I have to look at the exact date, but I have a feeling it's somewhere in September 2023. That's the first criteria that you have to check. The second criteria, if it is a full variable language or a limited variable language, the diagnostic coverage of the interface needs to be more than 60%. And that's more or less a giveaway. That means if you would have an interface that is using a firmware-based interface, or it is a programmable interface, like as an example, a safety PLC, the diagnostic coverage is typically always more than 60%, so that is a giveaway. The third one could be a challenge. You need to show your data uncertainties. You need to show your data confidence needs to be more than 70%. And you need to prove also that your prior use data is based on performance evidence in similar operating environments. Assuming that you can prove all this, well, then you can jump into table 6, which is a table we showed you before. Alternatively, you don't have your own data, you call your vendor. You call your vendor, and your vendor has two options. The vendor has an option to go by the left method, number 1. Assume it's a new product, GMI brings out a new product, there is no install base, that's the only road 1H they can follow. And then they have to do an FMEA or FMEDA, they have to determine the safe failure fraction and or diagnostic coverage. They also have a normative requirement by the IEC61508 edition 2 to prove you the systematic capability. That means any vendor with a new product since April 2010 needs, besides the SIR level, needs to tell you in their safety manual what is their systematic capability. And the safety manual is a normative requirement. So in a nutshell, a certificate between brackets is not normative requirement. That's just a add-on. We need to have a safety manual normative required by the IEC61508. And in that safety manual will all be the safe failure fraction diagnostic coverage, will be systematic capability, will be a type A or type B definition, and also will be a probability to fail on demand average factor or a PFD in there, or a PFH in that safety manual. If you have selected road 1H, or if that is the vendor product that you will buy, then you are able to use here type A or type B or table 2 and table 3 that we have been mentioning before of the IEC61508 with the same definition. Here the leading indicator to select the correct quantity of interfaces is your safe failure fraction and or your diagnostic coverage. And based on type A or type B interface, you will have to select HFT0, HFT1 or HFT2 enabled for you to achieve your SIR level. And last but not least, if the end user is calling the manufacturer and the manufacturer will tell you that their product is based on road 2H, that means the manufacturer needs to prove that they collected from installed bases quality field feedback data. That means the manufacturer needs to show feedback in similar application environments. That's one criteria. Second, the criteria will be requiring the manufacturers to collect the data based on those two quality standards. They need to show a confidence factor of 90%, whereas the end user was only 70%. Here they require 20 additional percentage on the confidence factors. And additionally, typically what they will do is they do an evaluation based on the amount of feedback, based on some additional tests they have been doing on their, let's say, interfaces. That is the result that the expert judgment will then make a decision. Can they use this for a SIL 1, a SIL 2, or for a SIL 3 based on the road to H? If it is a road to H component, then you can again use the table 6, which is a simplified table. So in closing or in summary, you may notice on the second table here on the right hand side, there is no safe beta fraction, there is no diagnostic coverage. When you have safe beta diagnostic coverage, it's typically only in the road 1H criteria. Right, so theory is the left hand side, that's starting from scratch, or some manufacturers will still maintain that although they do have some feedback, they still will prefer here to go to road 1H. That's all the theory approach. On the road to H, if it is proven in use or prior use, we need quality feedback data. But the main problem that we face in the industry, who of the end users have quality fair feedback data? I have a large book of excuses why people cannot collect data. No time, no interest, no competency, no people available, or whatever was their excuse. Whereas we have a very small example in the industry of where our end users really doing good collection with fair data analysis or root cause analysis if something goes wrong. So field fair data is one of the weakest, or quality data is one of the weakest items that we do face in the last 10 to 15 years. So my colleague Gabriele has launched a second poll. That's the second interaction that we want from you. And here I'm playing on the words safety availability versus production availability. And you may remember I showed you a slide with two columns. One was safety availability, the other one was production availability. And here only one answer is again the most complete and the most correct answer in this entire row. So one out of two and 2 out of 3 are the same for production availability. It's answer A. Answer B. 1 out of 2 is better for safety availability than a 2 out of 3. Answer C. 2 out of 3 provides both safety and production availability. Answer D. A 2 out of 2 and a 2 out of 3 provides the same safety and production availability. And last but not least, a 2 out of 2, 2 out of 3, or a 2 out of 4. All architectures provide the maximum safety and the maximum production availability. So we need a few more clicks again, enabled to show that people are still alert and still following the webinar, which I'm quite happy with the number of people that joined us today. I think it's maybe because it's the early one in 2024 that we have lots of people coming in, which is only pleasing us, of course. So we have 59% so far clicking, 67, so we are getting there. Okay, one more click, and I think we should close it, the deal. All right, we can stop it. Okay. Gabriele, you can share the results. All right, so I got 10% saying that 1 out of 2 and 2 out of 3 are the same for production availability. Well, unfortunately, this is not correct. A 1 out of 2 and a 2 out of 3 are the same for safety availability because they both can tolerate 1 day of failure. However, a 1 out of 2 cannot tolerate the superior strip. That means only a 2 out of 3 can also provide you a production availability by dealing with 1 superior strip. So that is why answer A was not correct. Then we have 30% answering that a 1 out of 2 is better for safety availability than a 2 out of 3. Well, I just explained you. A 1 out of 2 and a 2 out of 3 are the same for safety availability. They can both tolerate only 1 danger failure. That means answer B was also not correct. Therefore, We have 30% answering 2 out of 3 provide both safety and production availability, and that sounds quite good to me. So I would say that is the most and the best answer that you could have selected. And then we had 10%, 2 out of 2 and 2 out of 3 provide the same safety and production availability, while a 2 out of 2 has never a safety availability. You have to, but you need to. So you have no safety availability. If I have a pipeline and I'm putting 10 valves as fail open valves to drain a reactor, I have to open all 10 valves, so I have not achieved anything on safety, but I have tremendously achieved production availability. That is why a 2 out of 2 can never achieve a safety availability. Right, I go stop sharing and I will continue. Right, well, we will summarize. As we mentioned before, one of the targets is to help the industry with some awareness. So we also deliver, of course, some physical support or some virtual support that we like to do now also. So we have 61511, plus also we have the 62443, which is to do with the OT security for cybersecurity support. We do virtual as well as classroom and structure-led trainings. That means one of the main targets is still that GMI is organizing for us the TOV Rhineland accredited competency review training programs. And we have several. We have the traditional function safety engineer, which today I think by numbers worldwide in the last 20 years we have, because this year 2024 we are existing 20 years in the program. I was one of the first trainers on the program, active and still active today. The Function Safety Engineer SIS program has about 20,000 engineers worldwide, roughly. We have the Cybersecurity Fundamentals and the Security Risk Assessment course, which is both or combined a 1-week course or a separate 2 separate week course in 3.5 days. But more and more we are delivering this now in a combined fundamentals in 1 day with a review, and then security risk assessment in the remaining 3 days with an exam on the last day. You may or may not have this book. If you go on the website of GMI, you will see that you can actually require or request one of those books. That's the SIL manual in the 4th edition, where myself as a co-author of the book I wrote or rewrote the, no, actually I started from scratch. I wrote chapter 7 as the executive summary for 61511, and I wrote chapter 8 as the safety requirement specification with one safety loop. Right, I will swap to the question and answer quickly. I see that I'm running out of time, which is normal, because I always speak too much, I've been told, often. But that's sometimes appreciated by the engineers following the webinars. Right, let me share you this screen, and then, as I said before, we collect some questions and some answers during the pre-registration for the webinar. And the first question that we got was, what are the minimum requirements, not recommendations for SIL 2, question mark, including software development? So when I read the question, I noticed that there were 2 items in there that I could recognize that I would like to answer. So I prepared this table here, or I prepared this answer, which was already mentioned in the webinar, so we can be quite quick on the answer. But the first part of my answer is focusing on the 61511. And since the, let's say, participant was asking the question specific for the SIL 2, the IEC61511 is typically not dealing with software, but is dealing with application programming of a safety PLC logic control solver. In other words, you are programming a PLC logic solver enabled to control your interlocks or enabled to program your interlocks. And we know that the application programming safety PLCs on the industry today are going up to maximum SIL 3. There are some specific vendors only going up to maximum SIL 2, so but you can, in both safety PLCs, you can program SIL 1, and if it is a SIL 2 PLC, only maximum SIL 2, but the majority are all providing you with SIL 3 PLC, so you can go up to maximum SIL 3 in your logic solver. Now, the minimum requirements for hardware technical constraint, as already also mentioned, goes up to maximum SIL4. And for SIL4, they require an HFT equal to 2. And for those who wants to read it into the 61511 standard ISA or IEC, you have to go to part 11, requirement 4.5. That is where you will see this table number 6 with the explanation behind the table. Now, very specific, because I recognize that the participant was asking the word software. They did not ask us the word application programming. And I thought maybe the engineer is asking the question because maybe they want to use something called based on prior use. So if you go in the same standard, part number 1, which is the normative section of the standard, and you go again to chapter 11, which is your design and engineering, and you go then to item 5.5.5, that is where you will see the following sentence. For a SIL1 or for a SIL2 application, a safety configured programmable electronic logic solver may be used, provided that all of the following additional provisions are met. And there are 4 conditions that you will have to meet. Now, if you ask me, this doesn't make sense to me at all, because I do not know any end user today that is using a programmable logic solver based on prior use. That would mean you would have bought maybe years ago a normal PLC, nothing safety related, and because you love the PLC so much and you have so good record for it, you would say, you know what? I gonna claim for this normal PLC, I gonna make it a SIL2 PLC. However, there is an escape route here saying in 5.5.5, if you are understanding all of the unsafe failure modes of that PLC, which is not SIL rated, and you use specific techniques for safety configuration that address to identify your failure modes, that means you are already becoming a safety expert, and you will use a normal PLC and you will start to define your failure modes, which I would doubt, but okay, fine, it's possible. Miracles exist, excuses exist. The embedded software has good history of use of safety application that blows completely my mind. And remember, I'm only having a limited number of 30 years experience in the safety industry, in the process industry. If someone would ask me to use a normal PLC, and I have good software history of use for safety application of the firmware in that PLC, well, that blows completely my mind, but assume that you could prove that also. And the last one, you can prove protection against unauthorized and unintended modification. That means you may have a certain scheme on how you will start to modify that PLC configuration. Well, if you can fulfill all that, be my guest. And you start to claim SIL2. Do me a favor and ask me as your inspector, assessor that will do an assessment on your safety installation. And I may show you a few tricks out of my sleeves where I can run a bus through the statements. But if you would like to do that, I would say go ahead and you could actually do this. Right. Second question, and there is another question coming in from someone that I do recognize the name. And the question is the book or the text available in German? I will send you an answer on this, and I will copy also Gabriele because there is a solution for that. Right. The second question that was pre-registered, what is the difference between Road 1H and Road 2H from a minimum technical constraint required and how it impacts the SIL? Well, I don't have to spend much time because I just explained it already in the webinar. If you know and understand how to, or what is the background on the definitions or conditions of this road selection, that is where you can actually follow then Road 1H, Road 2H, and select your minimum HFT. And the last one, for SIL2, which HFT is required for low demand and high demand, question mark? Which HFT is required for low demand, high demand, question mark? Which is the criteria of a SIF to be considered high demand or low demand in IEC 61511? Question mark. It's a long question. I see already two different questions here. And how to select the criteria for a SIF for high demand and or continuous mode tanks. Okay. Well, often writing a question is easier than trying to create an answer. What I've done is I focus here on the definition of low, high, and continuous mode, which I also explained already, but I want to give you here as a text, and I give you the reference. If you go into chapter 3, which is the definition and abbreviations of the IEC 61511, part number 1 is still the normative section. The three definitions are being described as followed. What is a low demand? A low demand for a SIF operation mode is described as the mode of operations where the SIF is only performed on demand in order to transfer the process into a specific safe state, and where the demand or the frequency of the demand, and remember, this is the hazard that is demanding the safety loop. It's not a wanted demand, it's not a proof test demand, it's purely a demand coming from a hazard, is no greater than 1 per year. But I want to highlight a low demand in the 61511 today can only be expressed with a PFD average only. And what is a PFD average? Well, PFD average is clearly only depending on your proof test interval and on your proof test coverage factors. Second one is a high demand mode definition. Well, there the mode of operation is where the SIF is only performed again on demand, and remember, it's again your hazard demand, in order to transfer your process into a specific safe state. But here, and where the frequency of your demand is greater than once per year, where opposite here was no greater than once per year. That means if your hazard is happening more than once per year, that is a definition in the standard 61511 for high demand, which is part of a demand mode still of the 61511. And strangely, what happened here on the high demand mode, if for those specialists in this webinar listening in, if you remember, I'm just looking at the participants, if you remember when the amendment came down in 2017 of the 61511 edition 2, that is where at this moment of time, it was I think in August 2017, they moved the high demand mode from the demand mode table back into the other side, which was belonging under the PFH or probability to fail per hour, which is still the column for a continuous mode. So in other words, the high demand mode today in 61511 can be expressed in both PFD average or in PFH, which is the probability to fail per hour. And here then we have the continuous mode, the mode of operations where the SIF retains the process in a safe state as part of the normal operation. That's only in PFH. I did not mention much about continuous mode yet. Continuous mode is a very unique, is a very special case, which is very seldom found in the process industry. Low demand, high demand are typically all your safety loops driven by a digital output. A digital output demanding your valve to go open or close or to start or stop your motor. That's always with digital output modules. Continuous mode can never be done with a digital output, because there the functionality is saying the mode of operation needs to retain the process in a safe state as part of normal operation. And that's a classical example, or classical, that's an extreme example of an analog output, accelerated output, driving a device, maintaining your safety loop to retain the process in a safe state. And the example giving by the technical report 4 from the IEC61511 is, for instance, when you have an analog output driving a cooling of a skin of a reactor, and your batch of the reactor needs to maintain a certain temperature to cool down the production, well, that could be potentially a continuous mode. I'm getting here an example from a participant, say metro railway is which type of a demand? Well, I do not know what metro railway application you are discussing. You are discussing here closing and opening of a door? You are discussing here the signaling of the lights? you are discussing here the opening and closing of a barriers. What is your question to this participant? If you answer on time, I may give you a decent answer. Otherwise, I just have to assume an answer, and I hate to make assumptions in safety. Right, Gabriele? Sorry for the delay.
Yes,
We have
no,
9.
it's okay. There was another question about someone asking if the book is available in German. The
Yes,
SIL
I
book
have
it's only
seen that.
available in English. Okay, if you need any document, there is still the communication@gminternational.com. You can write and they can help you with that, and then we can launch.
Yeah, Gabriele,
Class.
this participant is someone that was recently, and I know the person in my training course, so
Class, okay.
I'll answer them, and I will copy you and the people from
Thanks.
GMI, because there is a solution which I can think of that I can present to this participant. Okay, so I got the second question coming in a little bit rephrased. Third question about Metro Railway is SCADA designed for tunnel ventilation in underground metro system. Right, we're getting there. It's the tunnel ventilation as a safety function, I would assume. So let's just assume there is fire in the tunnel and the smoke is filling the tunnel and the metro is driving into the tunnel, and we don't want to have that. So we want to isolate the tunnel. That is one example I can think of. So that would be a demand mode for me to demand to barriers to close the tunnel that the train cannot drive in. Assume the train is inside the tunnel. When the fire will start to happen, well, then, of course, we need to distinguish the fire. That means we have to start a deluge system. That means, first of all, the question will be the demand mode. Will be the fire be detectable? That's the first question. Or the smoke is detectable. Then your tunnel ventilation is your mitigation system, where your tunnel ventilation will mitigate the smoke from the tunnel. So again, to start the ventilation, to start to motor the engine, that's again a demand mode for me. So until here, I have found nothing in my explanation that I can think about a potential continuous mode. So it's all still demand modes for me. So I hope this quick analysis was sufficient. In the meantime, I think the poll is nearly finished. Is finished. I think we should end the poll. You can share the results.
We can share the results. Sure, we can. There we are.
All right. So you can read the summary, Gabriele. That is typically the task for the GMI people and not for me.
Just to let you know that most of the people participating said that it was an excellent webinar. Don't think it's good, but I think that everybody's pretty much happy about your performance. Yes.
Yeah. I still wait until someone's saying it's not in line with the expectation, because then it means they have probably joined the wrong one or the wrong webinar. All right. Well, thank you, GMI. Thank you for all the participants. And as I said, let's just very quickly before you leave it. I see here this participant keeps on. I would offer this participant to send me an email. Fans will start to direct the smoke, or to extract the smoke. Bit confusing for me. Fire smokes are detectable. Fans will direct the smoke away from the passenger for evacuation. Exactly. So it confirms what my assumption was, that even when the smoke is being detected or measured or being recognized, you will start the fans to try to get the smoke out of the area where maybe the people have to evacuate. So this is still called all a demand mode for me. And I do hope the tunnel will not have a high demand mode. That means that the fire will not be more than once per year in that, let's say, metro installation. All right, that's it for me. I would say thank you, everyone. Grazie mille, Gabriele. We hopefully will meet somewhere in the future. We never know.
Yep.
And up to the next webinar. I think there is another one coming up soon again, by memory. All right, thank you. I will stop the webinar. Thank you. Ciao, ciao.
Have a nice day.
You too. Thank you. Bye-bye.
Bye-bye.